In the last segment, we talked about simulation models in enormous generality. Today I want to get more specific and look at an example of how a simulation model can be built and get some practice in designing classes along the way. So let's start by looking at the notion of Brownian motion, as shown by these red and blue dots moving on your screen. In 1827, the Scottish botanist Robert Brown observed that pollen particles suspended in water seemed to float around at random. He had no plausible explanation for this so-called Brownian motion and made no attempts to model it mathematically. A clear mathematical model of the phenomenon was first presented in 1900 in Louis Bachelier's doctoral thesis, The Theory of Speculation. However, unfortunately for Louis, since this thesis dealt with the then very disreputable problem of understanding financial markets, it was largely ignored by respectable academics, and in fact, he struggled to even get a job. 5 years later, however, in 1905, Albert Einstein, then a young man, brought this kind of stochastic thinking to the world of physics, with a mathematical model almost the same as Bachelier's, and a description of how that model could be used to confirm the existence of atoms. For reasons certainly lost on me, people seemed to think that understanding physics was more important than making money. I guess the times were different. Brownian motion is an example of something that has come to be called a random walk. Random walks are widely used to model physical processes, e.g. heat diffusion, biological processes, for example, the kinetic displacement of RNA from heteroduplexes by DNA. I hope some of you know what that means. I'm not sure I do. And social processes. For example, getting back to Bachelier, the movements of the stock market. What I want to do now, though, is look at an example of a random walk that is actually a walk. Imagine, if you can, a drunken farmer standing in the middle of the field, and every second he takes one step in a random direction. Now, I want you to ponder the question, what is the expected distance from the origin in, say, 1,000 seconds? More generally, if the farmer takes many steps, is he likely to move ever further from the origin? Or is he more likely to wander back to the origin over and over again and end up not far from where he started? Let's write a simulation to find out. But before we do that, before we build any complicated computation, it's always a good idea to develop some intuition about the situation the program is intended to model. Let's start by sketching a simple model of the situation using Cartesian coordinates. Assume that the farmer is standing in a field where the grass has mysteriously been cut to resemble a piece of graph paper. Let's assume further, put the farmer right here in the middle, assume further that each step the farmer takes is of length 1 and is parallel to either the x or y axis. Clearly, this is an oversimplification, but it's a common approach to building simulation models. We start with something simple and then add complexity a little bit at a time. All right, after one step, the farmer will be either here, or here, or here, or here. So we see that after one step, the farmer is exactly 1 unit away from where he started. Let's look at the second step. Without loss of generality, we'll assume that he took this first step eastward. It will be symmetric if we went in a different direction. After the second step, he could be right back where he started, that is to say 0 units away, or he could be another step east, 2 units away, each of those a quarter of the time, and half the time he'll be there or there. How far away is that? Well, that's the square root of 2 units away. How do we know that? Well, let's look at our old friend, the Pythagorean theorem. We can look at it here, and we know that a squared is equal to a squared plus b squared is equal to c squared. Therefore, c is equal to the square root of a squared plus b squared. And if we go back here, we look at, say, that x, we see that a is 1 and b is 1, and therefore this distance here is going to be the square root of 2. All right, I could now look at a third step and keep drawing circles all over the place, but it's starting to get pretty complicated. And that suggests to me that it's time to stop drawing pictures, and you'll probably be relieved given my drawing ability, and instead start writing code. Build a simulation that will actually give us the answer we want. Okay, let's give it a shot. Before we do, what's your intuition? Give it a minute, think about it. My intuition is that since half the time, more than half the time here, after 2 steps, the farmer is further away from the origin than after 1 step, maybe the longer he walks, the further he'll be. I'm not positive, but that's my guess going into the simulation. All right, on to the coding. But before we write the simulation, as usual, we want to try to invent some classes that correspond to the types of things that appear in the situation we are attempting to model. 3 classes seem potentially useful. We probably want a class location, because after all, that's mostly what we've been talking about, is the location of the drunken farmer. We probably want a class field corresponding to the graph paper we drew. And surely we're going to need something corresponding to a drunk, because that's going to have to model the movements. Now let's look at each of those classes. Come over to the code and look at class location. It's very simple. It's got an initialization. But even here, we see that a decision has been made. As simple as it is, we see that a location is going to have only X and Y coordinates. That tells us that it's going to be a 2-dimensional field. We're modeling a farmer, not, well, say a pigeon. There is no ability for the farmer to fly up in the Z coordinate. Also, it looks like perhaps we're ready to generalize our notion of moving due east, west, north, or south, because we're allowing X and Y to be floats. We've got move, which takes a self, delta X and delta Y, and returns a new location in which we've incremented X and Y by the delta. Note that the deltas could be negative, so this isn't saying that we're always moving in one or another direction. We can get X, we can get Y, and then here we're using the good old Pythagorean theorem, as we've just seen, to find the distance. And finally, we have a way to print the location. So reviewing, the notable aspects of location are 2 dimensions, no X and no Y, no built-in assumption about directions. That's because our delta X and delta Y are floats. All right, moving on, let's look at our next interesting type. That's going to be field. Fields, like locations, are also quite simple. We can initialize them. We can add a drunk to the field. We can move the drunk. This is probably the only really interesting function that we have here in fields, interesting method. So we say if the drunk is not already there, then we'll raise an exception. Otherwise, we'll take a step. What does that mean? We don't know yet. That depends upon the kind of drunk we're looking at, and that will allow us to take a step, and that will return a distance along the X direction and the Y direction. We'll get the current location, and then we'll update the current location with whatever we got from drunk.takeStep. So what are the notable aspects of class field that we might look at? Well, one thing we see about fields is that there can be many drunks. We might or might not choose to use that. There can be many drunks in the field. And furthermore, it seems to be that the drunks can be at the same location. We've not put in any restrictions about where the drunks are relative to each other. A final thing we'll notice is the field seems to be unbounded. We've said nothing about the drunk falling off the edge of the field or running into a fence. Again, these are simplifications which we may choose to remove later. The final class is actually 2 classes, and since it's a little bit complicated and I want to show you things about it, I'm going to look at them over here on the PowerPoint rather than on the idle window. As we guessed, I had a class drunk, but look how simple it is. The only thing that drunk does is it has a name and it can print the name. What we see here is really drunk is what we before called an abstract class. It's not intended to do anything useful by itself. It's intended to be subclassed to give us different kinds of drunks. And as we'll see, not in this segment, but in a future segment, we can use it to create some rather interesting and divergent behaviors depending upon the predilections of individual drunks. This segment will look at only one drunk, one class of drunk, and I'm going to call that the usual drunk. That's the kind of drunk we've been talking about so far. The most important thing to see here is that I'm importing class random. Most programming languages, including Python, include simple ways to write programs that use randomness. When we need randomness in a Python program, we import the class random, and that supplies us with a whole variety of useful functions. Here we're only using one. We're using the function random.choice. Random.choice has its argument a sequence, and at random chooses a single element of that sequence. With equal probability, it might choose any element. So for example, if I were to look at something like random.choice of range 3, it would at random return an integer in the range, what? 0 to 2, because we know that's the sequence that range 3 generates. Here, it will return a random element of step.choices, which we define to be a list of tuples corresponding to the steps in the north, south, east, and west direction. So for example, 0, 0 is a step north, 0 minus 1 is a step south, a step east, and a step west. With that, I'll stop, and in the next segment, we'll use these classes to start building our first interesting simulation.